Assalamualaikum and good day to everyone. Today, I will present my study on Acinetobacter baumannii, a gram-negative bacterium that has become a significant hospital-acquired pathogen. It is responsible for approximately 1 million infections annually, with particularly high mortality rates in intensive care units. What makes A. baumannii especially concerning is that it belongs to the escape group of pathogens. These organisms are known for their ability to evade antibiotic treatments, posing severe challenges to global healthcare. This study is important because A. baumannii has developed mechanisms such as biofilm formation and antibiotic resistance, which make it highly persistent in healthcare settings. Biofilm act as protective shields, enabling bacteria to survive harsh conditions and resist treatments. Moreover, multi-drug resistant strains of A. baumannii have emerged worldwide, leading the World Health Organization and the Centers for Disease Control and Prevention to classify it as a high priority pathogen. The challenges posed by A. baumannii can be summarized into three main problems. Firstly, its ability to form biofilms allows it to cause persistent infections that are difficult to treat. Secondly, its multi-drug resistance severely limits the effectiveness of current antibiotics. Finally, there is a significant gap in understanding the molecular mechanisms linking biofilm formation and resistance, which hinders the development of effective therapies. To address these issues, this study has three objectives: to investigate the molecular mechanisms behind biofilm formation, to assess the patterns and mechanism of antibiotic resistance, and to explore emerging therapeutic strategies that can overcome these challenges. Biofilm formation is a complex process that begins with bacterial adhesion to surface using structures like pili and fibrille. This is followed by the production of an extracellular polymeric substance, or EPS for short, which provides mechanical stability and protects the bacteria from immune responses and antibiotics. Quorum sensing, a communication mechanism between bacterial cells, also plays a crucial role in regulating biofilm development. Research has shown that environmental factors such as temperature influence biofilm formation, with cooler temperatures promoting stronger biofilms. In terms of antibiotic resistant mechanisms, A. baumannii has developed several strategies. It produces B-lactamase such as oxotype carbametases, which degrade antibiotics and render them ineffective. Efflux pump like 8-ABC actively expel antibiotics from bacterial cells, reducing drug efficacy. Additionally, membrane alterations limit the entry of antibiotics into bacterial cells. These mechanisms are particularly prevalent in ICU settings, where resistance rates exceed 70%, creating a significant treatment challenges. To combat these challenges, novel therapeutic strategies have been proposed. Phage therapy uses bacteriophage to selectively target and destroy A. baumannii, including bacteria within biofilms. Immunotherapy involves monoclonal antibodies and vaccines that enhance the immune system's ability to fight the pathogens. New antibiotics such as cefiderocol and plazomicin are specifically designed to target multi-drug resistant strains. Combination therapies, which integrate these approaches, have shown promising results, though challenges like cost and scalability remains. Resistance patterns vary globally. For example, resistance rates in Asia and parts of the Middle East exceed 70%, while Oceania reports lower rates below 10%. ICUs are hotspot for resistance due to frequent antibiotic uses. To address this, international collaboration and surveillance are crucial. Shared data from organizations like WHO, help design tailored infection control strategies, reducing the global burden of air money. To summarize how this study addresses the objective, first, it identifies biofilm formation as a process involving additions, EPS production, and quorum sensing, which collectively enhance bacterial survival and resistance. Second, it highlights resistant mechanisms such as B. lactamase, efflux pumps, and membrane alterations, with regional variability requiring tailored interventions. Finally, it explores emerging strategies like phage therapy, immunotherapy, and new antibiotics, which show potential for overcoming these challenges, though further research is needed to optimize their implementation. In conclusion, Acinetobacter baumannii poses a major threat to healthcare systems due to its ability to form biofilms and develop multi-drug resistance. This factor complicate treatment and highlight the urgent need for innovative solutions. I recommend developing therapies targeting biofilm components such as quorum sensing inhibitors and EPS degrading agents, enhancing global surveillance and diagnostic to monitor resistant patterns, and promoting multidisciplinary collaboration to improve infection prevention and treatment. By addressing these areas, we can take significant steps toward controlling A. baumannii infections. Finally, these are the key references that inform this study covering biofilm mechanism, resistant patterns, and therapeutic strategies. Thank you for your attention, and I'm happy to answer any question you may have.